Hello, my name is Aya. Our topic is Reconfigurable Computing. I'll be given a brief introduction about what Reconfigurable Computing is and the history of how it developed throughout time. Reconfigurable computing is a computing architecture consisting of a general-purpose processor and reconfigurable hardware. Operations and software are performed using general-purpose processor or GPPs. It is known to be flexible, but it lacks in performance because it cannot compute in parallel. GPPs are programmed to execute a set of instructions sequentially to perform a computation. Only software is altered after fabrication, leaving the hardware without change. Operations and hardware are performed using application-specific integrated circuits, or ASICs. They're known for their high performance. They're very fast and efficient when it comes to executing specific tasks. After fabrication, the circuit or the device structure will not be modified. So what a reconfigurable device does is merge between the flexibility of GPPs and the high performance of ASICs. Role of FPGA in reconfigurable computing. FPGAs, or field programmable gate arrays, they were introduced to the world in the mid-80s, 1984 to be specific. FPGAs are silicon chips comprised of logic blocks, a programmable interconnection network to customize operations for a specific application, and a set of input-output cells. It offers high-performance computing with reprogramming capability. The interconnects allow the FPGA to accommodate into the required functionality without manufacturing new chips or having to make any changes in the hardware to reprogram the FPGA. FPGAs can handle multiple operations, making them capable of parallel processing, which is beneficial for processing large data sets in real time. History of reconfigurable computing. The first notion of reconfigurable computing date back to the 60s, where Gerald Estron paper, Organization of Computer Systems, the Fixed plus Variable Structure Computer, suggested the idea of a computer made from a standard processor and an array of reconfigurable hardware, and that was responsible for the invention of FPGAs in 1984 by Xilinx. Programmable Active Memory, PAM, and systolic processor with a large array of hardware, Splash, were one of the early platforms of reconfigurable computing. PAM is controlled by a standard processor which can be reconfigured into a large number of application-specific circuits. It also blends between hardware performance and software versatility. Splash is a programmable linear logic array that can be configured to suit the problem at hand. Splash contributed to DNA sequence analysis and pattern matching application, and that's because its domain is created on non-floating applications. Recent innovations in reconfigurable computing. Coarse-grained reconfigurable arrays is a more recent approach on reconfigurable architecture. CGRA is basically an array of processing elements interconnected by a 2D network, and it focuses on configurable blocks instead of singular logic gates. The reprogrammable, reconfigurable nature of FPGA lends itself well to a rapidly evolving AI landscape, allowing designers to test algorithms quickly and get to market fast and scale quickly. AI chips include graphics processing units, field programmable gate arrays, and an application-specific integrated circuit. The reason behind this excitement about AI is because AI chips are more efficient, run faster, and consume less energy than general-purpose CPUs.
Okay, now I will continue with the recommendations for improvement part. Development of software tools. FPGA is a complex and time-consuming process, so it is important to make high-level synthesis tools more accessible, user-friendly, and powerful. Energy efficient design. Energy efficiency should be in foreground for the systems that are running in energy constrained areas, or like FPGA. For this reason, coarse-grained reconfigurable arrays should be integrated into FPGAs to gain potential benefits. Security and prevention of hardware threats. Reconfigurable computing system may be vulnerable to hardware attacks. To prevent these attacks, it is important and critical to develop mechanisms like bitstream encryption, ID authentication, and access control. Okay, let's continue. Hardware operating system integration. Traditional operating systems are not designed to effectively support reconfigurable hardwares. In the future, new operating systems that supports dynamic reconfiguration of FPGAs and optimizes resource management has to be developed. Dissemination of cloud-based FPGA services. Reconfigurable computing in applications that requires high performance. Important to offer FPGAs as a service in cloud environments. Examples like Amazon EC2 F1 allows developers to use FPGA sources without dealing with hardware infrastructure. Automating validation and testing processes. Traditional hardware testing methods may be insufficient in these dynamic systems. For this reason, automated testing and verification tools specific to reconfigurable architectures need to be developed. Okay, let's continue with the conclusion. Flexibility plus high performance. FPGAs combine hardware customization with software flexibility, enabling size systems that are both optimized and expandable. Also, FPGAs provide the most efficient architecture for tasks thanks to their customizable structures. Parallel processing capability. FPGAs can perform many operations simultaneously, which is especially advantageous in areas such as big data, AI, and signal processing. Key application areas for FPGAs or reconfigurable computing. Real-time data processing, areas like finance, radar systems, automotive, AI acceleration, alternative to GPU, especially for deep learning operations. Embedded systems, customized solutions for energy-constrained and space-limited environments, and telecommunications, rapid prototyping and adaptive network solutions. Future prospects and strategic importance of FPGA. It can reach a wider user base with more user-friendly tools. Security solutions should be developed at the hardware level. Integration should be facilitated by developing common hardware-software design environments. Advances in accessibility, performance, and security will be achieved through interdisciplinary collaborations. Reconfigurable computing will play a strategic role in digital infrastructure of the future. Okay, that's all. Thanks for listening.